Hello guys, welcome to another video. Today we are going to do Unit 1, January 2025, Section 2. If you've not yet subscribed to my channel, please do. Please like and share it. And if you need help learning physics, please visit the website. I'll put it in the description, physicsandenglishtutors.online. And I'll be happy to help you. So let's move on to Section 2. Okay. So question 11. The mass of a car is 1850 kg. Some people sit in the car. The car then accelerates at 0.230 meters per second squared when the resultant force on the car is 460 newtons. Calculate the total mass of the people in the car. Okay, 3 marks. 1850 kg. So there's a car, and we know the mass of the car. We know the acceleration, and we know the resultant force. And we have to find the total mass of the people in the car. So it's a simple question. We can directly use Newton's second law, F is equal to ma. An important point about Newton's second law is remember that this force is not just like any force, it's the resultant force, which means it is the total force in the system. Like when you account for all of the forces, that is called the resultant force. Like a simple example would be if there are 200 newtons to the right and like 100 newtons to the left acting on a block, then the resultant force would be 200 minus 100 because they're in opposite directions, and the resultant force would be 100 newtons. So Newton's second law refers to the resultant force. Now over here, there's a car and there are people in the car. So the force acts on both of them. So it will be the mass of the car, mc, plus mass of the people, mp, times the acceleration. The force, the resultant force is 460. This is 1850. We do not know the mass of the people, and the acceleration is 0.230. So this will be 460 is equal to 1850 times 0.230 plus 0.230 times mass of the people. Let's do some simple math. 1850 times 0.230, that is 425.5. So this will be 460 minus 425.5 divided by 0.230. This gives me 150 kg. So the mass of the people is 150 kilograms. There you go. Simple use of Newton's second law. Question 12. A person on skis slides down a slope. The slope is at an angle of 14 degrees to the horizontal. The initial speed of the person is 7.1 meters per second as shown. The resistive forces acting on the person are negligible. Calculate the speed of the person after moving 15 meters down the slope. So we know the angle, we know the initial speed, we know the distance. And what do we need to find? We need to find the speed of the person after moving down the slope. So we are finding the final speed. Now, this brings to mind the very common SUAT equation. V squared is equal to U squared plus 2AS, right? But now, the trick here, and this is 3 marks, this question is 3 marks. The trick here is, now it's very common to think, like, since the person is moving in air, the acceleration should just be 9.81, right? Like some students might think this way, that acceleration should be this because, yeah, he's moving through air. But this is free fall acceleration. Like we can only consider the acceleration to be 9.81 when someone is freely falling in air. Like even whether they're going up, going down, but this person here is not freely falling. They are in contact with a slope. So we cannot use this acceleration here. We will have to find the acceleration. Now, for any such questions, where, this is very important, if the resistive forces, and that includes both friction and air resistance, if they are negligible and there is a slope question, okay, if the resistive forces, including friction and air resistance, are negligible and it's a slope question, the acceleration is always equal to g sine theta, theta being the angle. This will always be true as long as these are negligible. Now, how do I know that? Because let's draw on the diagram to understand how this works. So the person's weight acts straight down. Remember, even if a person is on a slope or no matter what weird angle they're at, the weight always acts straight downwards. Um, and then if you draw a line here, okay, so the normal force would be here. Why is the normal force like that? The normal force is always at right angles to an object, to the surface, right? So to the surface, it's at right angles to that. So we draw a line opposite to the normal force. If this angle is 14 degrees, then by trigonometry, like this would be 90, of course, and this would be 180 minus 90 and minus 40, and then this would be 40. That might have been weird, but I meant like this side would have just been 90 plus 40, and then 180 minus that. So that would be 76. So this angle is 76. And then this entire angle here would be 90, right? So if you know that this is 76, then 90 minus 76, what is that? 40. So that means this angle will be 40. Okay. Now I explained trigonometry here if somebody did not know why that angle would be 40. But you don't need to do the trigonometry part every time. Just remember, in any flow question, whatever the angle you have here would be the same angle that would be between this line and the line of weight, the line of action of weight. Okay, now, so we figured out the angle. Now, remember vectors, basic rules of vectors. So weight here will have two components. Because why do we need components here? Because the normal force and weight, look at them, they're neither parallel nor anti-parallel. What does that mean? They're not in the same direction and they're not in opposite directions either. And they're also not like just xy along the xy axis. Like let's say if the normal force was like this and weight was like this, in a very weird way. Okay, this is just a very weird example, but just try to understand what I'm saying. Like if you have forces, let's just take some random forces, F1 and F2, and one of them is in the x-axis and one of them is along the y-axis, you can just resolve them without dealing with components. But when forces act like this here, like normal and weight, they are at some weird angle. They're not parallel, they're not anti-parallel, they're not perpendicular either. Then you have to deal with components. So this part here would be the side adjacent to the angle. The side right next to the angle is always the cos component. So this would be weight times the cos theta, which is 40. And then the side opposite to the angle would be like this. This will be sine component. Some students remember it like the horizontal is always cos and the vertical is always sine. That is wrong. In some situations, that can be true. But the rule is adjacent to the angle, cos, opposite to the angle, sine. And this line that I drew, weight sine 14, look, I drew it parallel to the slope, okay? At least I tried to draw it parallel to the slope. Yeah, it does look parallel to the slope. Um, if you draw it, like let's say you draw it like this, perfectly horizontal, that would be wrong. Why? Because weight sine theta here is actually pulling the skier down. Whenever somebody is moving on a slope, the force that causes them to move down the slope is weight sine theta. So if you draw weight sine theta like this, you're actually saying there is a force acting like this, and which would be wrong. So that's why it's important to draw it in the right way, adjacent to the slope. Um, okay, so now we figured out the components, right? I was just trying to tell you how do I know that the acceleration will be g sine theta. So what force is pulling the person down? Weight sine theta. So let's write Newton's second law. F is equal to ma. F is the resultant force. The forces along the slope. How many forces are there along the slope? It's just weight sine 14. There is no other force. If there was friction or air resistance, we would count them, but they're not there. So the only force would be weight sine 14 here. Mass is on the other side and acceleration is on the other side. Now, what is weight equal to? It is equal to mg. So mg sine 14 is equal to ma. So mass would cancel out and acceleration is just g sine 40. So you see, in any question where there's a slope and friction, air resistance are ignored, then acceleration must be equal to g sine 40. Like there must not be any other force along the slope, opposite to the slope. Then acceleration will be equal to this. Now, I got into a lot of explanation here. I just did that because somebody might not be familiar with all this. So now this is the acceleration. Let's calculate it. 9.81 times sine 40. That is 2.37. And this is acceleration, so meters per second squared. Let's substitute it now in the Subat equation because we are trying to find the final speed of the skier. The initial speed was 7.1 squared plus 2 times 2.37 times the distance, which is 15. So this is 121.51, and we square root it to get 11.0 meters per second. So that's the speed of the skier. I hope that's clear. Moving on. Question 13. An escape lane can stop cars or trucks safely if the brakes stop working when moving downhill. The photograph shows an escape lane. The escape lane is made of sand and is horizontal. As shown below, the resistive force of the sand on a vehicle reduces the kinetic energy of the vehicle. Oops. As a truck enters the escape lane, the kinetic energy of the truck is 8 times 10 to the power 6 joules. The sand exerts an average resistive force of 3.5 times 10 power 5 newtons on the truck as the truck comes to rest. Calculate the distance moved by the truck on the escape lane. Lot of text. What's happening here? Um, so there is an escape lane. If a truck is going on this road and its brakes fail, so it wouldn't be able to stop itself. So one way for the driver to avoid any accidents is by steering the truck towards the escape lane. So when the truck goes on the escape lane, it's filled with sand. So that provides a lot of friction. So that friction, it has a much higher friction than the road. That friction stops the truck. And since there are no other vehicles on the escape lane, so there are no risks of accidents. Um, Now, the part A is 2 marks, and it tells us that there is a truck entering the escape lane, and its kinetic energy is this. The sand exerts an average resistive force. So the sand is exerting this force on the truck as the truck comes to rest. So the final velocity of the truck is 0. Calculate the distance moved by the truck on the escape lane. We have to find S, the distance. Right, how do we find that? We have kinetic energy, and this is when the truck has entered the escape lane. So we are just considered with this region. We're not considered with the slopey region, just this one. Okay. Um, to find the distance, think of it. Kinetic energy and force are provided to you, and you have to find distance. That sounds like a weird combination, but it isn't that weird. Force and distance together appear in the formula of work done. Work done is equal to force times distance. And work done is also equal to kinetic energy. Why is work done equal to kinetic energy? Because, sorry, because when you apply a force on an object and the object moves a certain distance, it moves, right? So it has kinetic energy. Anything that is moving has kinetic energy. So if you pushed something and it moved, basically you gave it kinetic energy. So work is equal to kinetic energy. Now, this example was specific to kinetic energy, but work is also equivalent to other energies as well. Um, so now let's just substitute the values. So distance would be 8 times 10 power 6 divided by 3.5 times 10 power 5. So distance is 22.9, sorry, yeah, 22.8 meters. So we can write that because the question is using two significant figures. 8.0 is two significant figures. 3.5 is two significant figures. So we write it. It's equal to 23 meters. All right. Part B. The resistive force exerted by the sand on a vehicle is proportional to the weight of the vehicle. The weight of a car is less than the weight of a truck. Explain how the deceleration of a car on the escape lane would compare with the deceleration of a truck. And this is 2 marks. The resistive force by the sand on a vehicle is proportional to weight of the vehicle. So the force that we are talking about, the resistive force, that is directly proportional to weight. What is weight? mg. So the force is directly proportional to mg. G is a constant, 9.81. So it's m that it's directly proportional to in one way. The weight of a car is less than the weight of a truck. Explain how the deceleration of a car on the escape lane would compare with the deceleration of a truck. So we have to say that, like, given this information, is the acceleration of a car while it's traveling on the escape lane less than the acceleration of the truck? Is it greater than the acceleration of the truck? Or is it equal to the acceleration of the truck? This is what we have to say. How does it compare, right? Um, so let's see. A common way of thinking would be if the weight of the car is less, then its acceleration should be less. Sorry, if the weight of the car is less, then the resistive force, which is proportional to the weight, should be less. And so acceleration should be less, right? That would be the most like direct thinking, but it's wrong. Um, we are specifically talking here about the resistive force. The resistive force is proportional to weight, right? Or it's proportional to mg, but it is not equal to mg, right? Why? Because like when something is proportional to something else, so to make it equal, this means there is some constant here that multiplies by this mg, and then this equation turns into an equality. Then this relation turns into an equality. Now, using Newton's second law, we can write the resulting force is equal to mass times acceleration, right? Now, what is the resultant force here? It's just think. The resistive force. Why? Because when the truck or the car, they're moving on the escape lane, there is no other force acting on the truck or the car. It's just the resistive force. So constant times mg is equal to ma. And what happens? The mass cancels out. And the acceleration is constant multiplied by g. Now, this is a general expression. It's valid for both the truck and the car. So for the car, it depends on the constant in g. For the truck, it depends on the constant in g. What does that tell you? This means acceleration of the car is equal to acceleration of the truck on the escape lane. Now, I can understand if this still feels confusing to some of you. And for that, you can think of another way. Like if you are like weirded out by this constant and you're thinking, what is this? It doesn't make sense. What is the resistive force that's acting on the truck or the car when it's moving on the escape lane? Like the question ends here, but this is an alternate explanation for anyone who is stuck on understanding this question. And I personally like this explanation more. the resistive force on is because of the sand, right? So what is it? It's friction. And what is the formula of friction? Uh, Coefficient of friction times the normal force. What is the normal force equal to on a flat road? The escape lane is flat, so it's just equal to the weight. So basically, this force here that we are not referring to by name is the friction. So if you now put friction in the Newton's second law equation, so like it is F is equal to ma, the resulting force is friction. So the mass cancels out and acceleration is just equal to coefficient of friction times g. So what does that tell you? Again, the acceleration depends on g, 9.81, that's a constant, both for the car and the truck. Mu, which is the coefficient of friction, that depends on the sand and the road, the surface of the road. So that's the same because it's the same escape lane. So the acceleration is the same for the car or the truck, right? So that is how this question makes sense. Like the only difference is here they do not refer to the force by name. Let me know what explanation you guys find better or easy to understand. Um, However, the like the first explanation would be preferred because that's what the mark scheme uses, and that also uses the terminologies of the question where they do not refer to the force as friction. I hope this part's clear. Um, okay, moving on to question 40. An air track is a straight tube with holes along its length. Air force through the holes lifts the gliders, preventing friction between the gliders and the air track. A teacher uses an air track and two gliders A and B to demonstrate the principle of conservation of linear momentum. Gliders A and B move towards each other and then collide. State how Newton's third law applies to the gliders during the collision. 1 mark. So what's happening? There are two gliders. They're moving on an air track. You can take this diagram for reference. And the gliders collide. Okay. And yeah, they collide. And now we have to say how Newton's third law applies to the gliders in this collision. So a very simple question, because what is Newton's third law? Every force has an equal and opposite reaction force. So during the collision, glider A exerts a force on glider B, and glider B exerts an equal and opposite force on glider A. That's it. That's Newton's third law. Um, Part B, gliders A and B have different masses and move at different velocities before the collision, as shown. So the picture is before the collision. The gliders stick together in the collision. A student predicts that the gliders will move to the left after the collision. Deduce whether the prediction is correct. 3 marks. So, a classic momentum question, conservation of momentum question. Um, we are given the mass of the first glider and its initial velocity the mass of the second glider, and its initial velocity. The student is saying that the gliders roll together, like the gliders actually stick together after the collision, and the student is predicting they'll go to the left. The directions are important in momentum questions because momentum is a vector. So again, using my convention, which is right is positive and left is negative. Okay, you can use the opposite as well. It's completely fine, but whatever convention you use, just always stick to that so you don't make mistakes. Um, so if the gliders, like let's assume for a second that the student is saying the truth, then the gliders, if they move to the left, that would mean their momentum, because momentum is a vector, would be negative if the student is true. So the momentum would be negative, and it would be the total momentum because the gliders stuck together. Uh, so let's find the total momentum. And if the total momentum is negative, the student is correct. If it is positive, then it means the gliders moved to the right, and the student is wrong. So total momentum of the gliders would be the momentum of glider A plus the momentum of glider B. The momentum of glider A would be mass of glider A plus velocity of glider A plus mass of glider B times velocity of glider B. Now, this is the mass is 0.15 times 0.32, 0.20 times. Important thing, glider B is moving to the left. In momentum questions and forces questions, you must be very careful with the directions. Glider B is moving to the left, that means its velocity is negative. So you will put a negative sign with 0.11 here. They will not tell you that in the question. You have to deduce that by yourself. So opposite directions, this means one of the velocities must be negative. And then since my convention is right is positive and left is negative, so I put negative with 0.11 because glider B is moving to the left. So let's just solve it. This gives me 0.026. And the unit of momentum is Newton seconds. Momentum has two units on a side note, Newton seconds or kilograms meters per second. They're both equal. You can use any of those. So the total momentum is positive, which means the gliders, when they stick together, afterwards they move to the right. So the gliders move to the right. Hence, the student is not correct. And we know that because this was positive. All right. Moving on to question 15. The Cruachan hydroelectric power station in Scotland is built inside a mountain. Water from a lake near the top of the mountain flows through straight pipes to a generator. The pipes have a length of 350 meters and are inclined at an angle of 55 degrees to the horizontal, as shown. The gravitational potential energy of the water in the lake is used to generate electrical power. In 1 minute, each pipe transfers 1,700 cubic meters of water to the generator. The density of the water in the lake is 1,100 kilograms per cubic meter. Show that the power transferred by the water in each pipe is about 88 megawatts. 5 marks. Lots of text again. Uh, so what is happening? This is a hydroelectric power station, and there's water in this lake. The water flows from the lake downwards through a pipe. Now we know the lengths of the pipes, we know the angle at which they're inclined. The energy that the water, when it flows down, because it's moving from a higher place to a lower place. So initially it had gravitational potential energy, a lot of gravitational potential energy, and then that decreases, and some other energy, which is the electrical energy store of the generator, that increases. Um, in 1 minute, we are also given the time. So we always use standard units, so kilograms, meters, and seconds. So we convert minutes to seconds. So each pipe transfers 1,700 cubic meters of water. Cubic meters, what is that? Volume. The density of the water in the lake is this, so we also know the density. And we have to find the power. Again, sounds like weird connections here, you know, density, volume, and then power. What's the connection? But let's think about power. What is power? Power is energy transferred over time or work done over time, right? So we have the time. That makes sense. Now, what energy is being transferred as the water moves down? It's moving from a higher place to a lower place. Gravitational potential energy. So the energy here is gravitational potential energy. And what is gravitational potential energy? mgh over time, right? So now we have the time, but we don't have the height or the mass. We cannot use the 350 meters, okay? Because for gravitational potential energy, we always use the height. So this thing. But we know the angle and the 350 meters, so we can find that. So if you use sine theta here, we can find the height. Sine theta is equal to, like, you can remember this by SOHCAHTOA. Opposite over hypotenuse. The opposite here is the height, actually. And the hypotenuse is the 350 meters. So the height would be 350 times sine of theta, and the theta is 55. So the height would be 286.7 meters. So we have the height. Now the missing thing is mass. We know the volume and we know the density. Density is mass over volume. So this implies that the mass will be equal to density times volume. The density is 1100, the volume is 1700. So the mass would be 1.87 times 10 power 6 kilograms. And now we substitute back. So power would be mass, which is 1.87 times 10 power 6 times g, 9.81 times height, 286.7 divided by the time, which is 60 seconds. So that is 87.6 times 10 power 6 watts, or 87.6 megawatts, because mega is 10 power 6, and this is approximately equal to 88 megawatts. So that's it. Moving on, part B. Water travels from the lake to the generator through 4 identical pipes. As water moves through the 4 pipes to the generator, the total power wasted is 256 megawatts. Calculate the efficiency of the power station. So what do we know? Wasted power, and that there are 4 pipes. And we have to find the efficiency. Efficiency is simple. It is just equal to useful power output over total power input, right? You could also write the same formula for energy, like useful energy output over useful energy input. But since we have power here, we are going with that. So, okay, now first, let's figure out what is the useful power output. Um, so now if you go back to the previous part, it said each pipe transfers 1700 cubic meters of water, and show that the power transferred by the water in each pipe. So the power that we found before, 88 megawatts, that was just for 1 pipe. We have to first find it for 4 pipes. So the power for 4 pipes would be 4 times 87.6 megawatts, right? So that would be 350.4 megawatts. And do we know any other information in the question? No. So that's the total power. Okay, so it's the power input. And how would we find the power output? We know the wasted power, so we'll subtract the wasted power from this number, right? So this is the total input, and the useful output would be the total input minus the wasted energy, power, sorry. So that would be 350.4 megawatts minus wasted power, which is 256 megawatts. So that is 94.4 megawatts. So now we find the efficiency. 94.4 megawatts over 350.4 megawatts. The reason why I am writing megawatts everywhere or saying it all the time, uh, it's because in such questions where you have like something in mega or some other prefix, sometimes students might use one thing in watts and another thing in megawatts. So make sure that all of them are consistent. So I get 0.27. That's the efficiency. Efficiency does not have any unit because it's a ratio. You divided two powers, the watts cancel out, and the percentage efficiency would be 27% because you just times it by 100. So that's it. So that's all for today. Um, if you guys have any questions from this video, anything that you're confused with, please leave a comment below and I'll get back to you. Also, again, please do like, share, and subscribe. And if you want to learn with me, visit the website physicsandenglishtutors.online. The link is below in the description. And see you again. Bye.